Hello, these are the exercises for one sample means with a t-distribution in section 4.2. So according to the American Time Use Survey, a typical American spends 154.8 minutes, 2.58 hours, per day watching television. A survey of 50 internet users in a time watching results in a time watching television per day of 138.7 minutes. The standard deviation of 76.5 minutes. Conduct the appropriate test to determine if internet users spend less time watching television at the 0.05 level of significance. So again, we have to first look at the parameter of interest. So we are talking about the mean time watching television per day. And so we are going to have our parameter of interest is mu. And what is believed to be the status quo is that a typical American is the status quo, and so that's 154 minutes, 0.8 minutes, okay? And we want to know the claim, test the claim, if internet users spend less time watching television. So we're going to have our mean watching of television being less than 154.8 minutes. So we have to go through and check our requirements. So our random sample or randomized experiment. So we come up here and look at our problem, and you see that we have a survey. So the survey, you are going to assume that it's done randomly. So we have this one done because we're assuming, it's an assumption that this survey was done with a randomized process. And that is a good assumption. You might want to look to see if you're reading this in a newspaper article or on the internet or in a journal, you may want to go through and see if it's a reputable source or not. But this survey, we're going to assume it was done randomly. Then we have to go through and check our requirements. Number 2 is that our population is normal, or our sample size is greater than or equal to the 30. So again, we don't know about the population and if the watching of television is normal or not. However, it's okay because we have a large enough sample of 50 internet users. Next, we have to go through and check the requirement that my sample size, which is 50, is less than or equal to 5% of my population size. So we had to divide this by 0.05. Solve the inequality for big N. And big N is going to be greater than or equal to 1,000. So you've got to think about what our population is. And in this case, we want to think that our population is, since we looked at a sample of 50 internet users, this population would be all internet users, which there are more than 1,000 of those. So that criteria is satisfied. Then you want to look what our alpha is, and that's our level of significance, which is our 0.05. So alpha is 0.05. Now we have to go through and find our test statistic and our p-value to compare it to alpha. So we come to GeoGebra and we recreate our null hypothesis here. Our null hypothesis was that mu equaled 154.8. Okay. This alternative hypothesis is going to be this exact same statement, but with a different inequality. Instead of an equals, we're going to have a less than, greater than, and does not equal. So we come back here and look at this, and we have a less than. So we need to change this to a less than. Then our sample mean, our sample standard deviation, and our sample size are these next blanks. And those are given to us here in the problem, our sample mean, our sample standard deviation, and our sample size. So we go recreate that in our GeoGebra inputs, and the mean was 138.7. Our sample standard deviation was 76.5, and our sample size was 50. and then we get our output right here. So my test statistic is my t, so it's a negative 1.49, and my p-value is this p, so 0.0716. So my t is a negative 1.49, and my p-value was 0.0716. So then we compare our p-value to our alpha. Our alpha is 0.05, my p-value is 0.0716, my p-value is greater, and so we're going to fail to reject our null hypothesis. So we fail to reject H naught. So there's insufficient evidence to believe our claim is true. And so we have insufficient evidence to conclude that internet users have a mean time spent watching TV less than a typical American. Okay, we don't have enough evidence to conclude that, and therefore we're going to maintain our belief in the status quo. So we're going to recompute this test statistic and p-value with everything being the same, except for instead of our sample size being 50, we're going to get a larger sample size and have a sample size of 100. Okay. So we're basically doing this exact same procedure, but we're changing this one statistic from a sample size of 50 to a sample size of 100. So look at my test statistic here and my p-value there to see what happens when we do that. They changed. So how do they change? So here, my test statistic is a negative 2.10, and my p-value became 0.0189. So they changed. So here, my t-value was a negative 2.10, and my p-value became 0.0189. So you can compare right here and right here to how they changed. So what we want to go through and look at this is what do you conclude about the impact of larger samples? So had we had this as our test statistic and p-value, we would compare our p-value to our alpha. Our p-value would be 0.0189. Our alpha is 0.05. That is less than, and now we would reject our null hypothesis. We would have sufficient evidence to conclude our null is true. We would have sufficient evidence to conclude that our alternative hypothesis is true. Okay, if this was our p-value. So what we want to go through and conclude is that all things being equal, so like our sample mean, our sample standard deviation, if there is more individuals in a sample, the p-value decreases. Okay, this means that it's going to be easier to get statistically significant results. Statistically significant results. Okay. And therefore, that's why you want to maybe look at practical significance when you have large sample sizes, etc., to see if there really is not only statistical significance, but practical significance that would make it worthwhile to continue on in that new direction.